Geometric probability is closely related to probability. When we discuss probability, we really need to understand what it means to figure out probability from a mathematical standpoint. Probability is a fraction of what's possible and what happened. So if I take this die, for example, this is a very common example of probability, and we are asking ourselves how many options are possible for what could happen. Well, the number of options possible for what could happen is 6 because it has 6 sides. So when I roll this die, I have only 6 things that could possibly happen. So if I ask myself the question, what are the chances that, or what is the probability that a 1 comes up, I take my number of outcomes and divide it by the number of possibilities that there are. In this case, 1 out of 6 possibilities. Let's see how that relates to geometric probability today. Like we talked about in the opening, probability is how many things satisfy what we want, say for example that 1 that we wanted to roll, out of the total number of outcomes. And so probability is equal to P. We're going to denote that as P. And that's going to be equal to the number of outcomes that we want. We'll call them events. And we're going to divide that by the number of possible outcomes. And we're going to call those the sample space. So that's everything that satisfies what we want. That rolling of that 1 divided by the total number of things that could possibly happen. 6. Okay? So geometric probability is going to lead us into a discussion of what is it when we define what we want and when we define what is possible. We're going to do that with length, angle measure, and area. Let's just look at an example of this. The sample space is everything that could happen. And because the sample space is everything that could happen, in that case where I had the die, everything that could happen was 6 things. And so if I'm talking about length, the sample space is going to be all the points on AD. So we might be talking about the probability of selecting a certain point on this segment. Well, the sample space is going to be all points on D. The event is going to be what I want to happen. Well, for example, if I highlight just this part, then my event is going to be what I want to happen. So my event is what I want to happen. Okay, and that's going to be all points on BC. Well, if I'm taking the part that I want over the total, my probability is going to be equal to the sample space over the outcome, or the event over the outcome. So it's going to be BC over AD, because it's what I want, say for example that 1 or BC over the total number of outcomes. And that's how geometric probability goes. It's basically what you want, or what's highlighted, over the total area. And so if I go to this angle measure here, my sample space is going to be all points on the circle. And if I'm trying to get something in this blue area, the event is all points in the blue region. This would be like an example of a spinner or something like that, where we take the amount of stuff in that region and put it over the total area. And so the easiest way to do this for a circle would be to say degree measure. So I'm going to put the measure of the angle to measure the blue angle over 360, because that's my total number of degrees in the whole circle. So that amount, that region, say 60 or 70 or 80 degrees over 360 is going to be my probability. My sample space for this one, if I'm still trying to get it into this shaded area, is going to be all points in the rectangle. Okay? And so if I'm looking at all points in the rectangle, my event is going to be that shaded area. And so if all points in the rectangle are my sample space, my event is all points in the triangle. Okay? So all points in the triangle are what I want to happen. Well, so my probability is equal to the area of triangle over the area of the rectangle. That's my probability. It's a fraction that is equal to the part that I want over the total. And so when I look at an example of this, I'm really just saying take this and apply it to a certain specific point. A point is chosen randomly on AD. Find the probability of each event. Well, the probability of each event is equal to my event over sample space. And in this case, my sample space is equal to part of the segment. So in this case, AC. So sample space equals AD, because notice I'm on AD. So my sample space is AD, which is equal to 4 plus 3 plus 5, which is 7 plus 5 is 12. So my sample space is 12. So my probability is something over 12. Well, what is my event in this case? In this case, my event equals AC, which is equal to 7. So my probability is 7 over 12. That gives me my probability. All right? So that's what I want to do, is I want to take the probability that I get what I want and put it over my total number of events. What about if the point is not on AB? Well, my sample space is equal to, well, still AD. My event is not AB, so that means that could be BC or CD. So my probability is equal to something out of 12 still, and that's going to be BC plus CD. Well, that's 3 plus 5 equals 8 over 12 equals 2/3. Okay? And so that's my sample probability right there. See if you can do this example C on your own. We'll talk about it in class. I'll give you a hint. You might be using 2 fractions for this one. Okay? Let's skip all the way down to example 3 here and look at a degree example. If you'll notice, I have a spinner here. And it has different regions coordinating with different colors. And so we're going to find the probability of each event. Say, for example, the pointer landing on red. Well, my sample space is going to be 360 degrees. So that's going to be my bottom number. So my probability is equal to event over sample space. And pointer landing on red is going to be 80 degrees. So what I do is I say 80 degrees over my sample space of 360. That gives me exactly what I want. Well, when I reduce that, I end up with 2 over 9, and that's my probability. I'm taking what I want to happen and putting it over the total number of outcomes. Let's look at this one over here. I know it's kind of separated now. Purple or blue. So my sample space is still equal to 360. So my probability is equal to purple or blue over 360. Well, purple is 75, blue is 60, and that's over 360. So that's going to give me 135 over 360. And that's going to give me what I want. When I reduce that fraction, I end up with 3 over 8 for my probability. What I want over the total number of outcomes is geometric probability. That's how simple it is. Okay, and so this can be applied to any question when you're at the carnival or anything like that, and you're trying to play those games where you pop the balloons. It's all geometric probability. What's the amount that I can hit that would win me the prize over the total amount that I could possibly hit? All right, guys, thanks for watching, and we'll see you next time.